Now, when we talk about influenzas, there are three families of influenza viruses: influenza A, B, and C. Influenza C tends to be rather unimportant. It's a mild disease. It's a bit like a common cold, usually infects children. Influenza B causes outbreaks and occasional epidemics, and influenza A is generally the more severe form: outbreaks, epidemics, and these worldwide pandemics on rare occasions, maybe about 3 a century. And when we look at the virus under the electron microscope, here is a picture of it magnified many millions of times. We see these little baggy structures with a hairy surface on them. And if we represent that schematically, it looks a little bit like this. This is rather simplified, but it has two proteins on the surface known as the hemagglutinin and neuraminidase. That's just important in terms of nomenclature. They're the H and the N that we often hear described as an H3N2 virus or an H3N1 virus. And I've shown here that the genetic material in the virus is RNA. It's in separate pieces, and it's all bound up in a lipid envelope. And these are important when we come to consider the properties of the virus. Influenza A has lots of different subtypes based on these different H's and N's. They've actually evolved in birds, but they can become established in humans and other species. Influenza B is just one big family of viruses. When we look at the naming of influenza viruses, the naming is based on the type of virus, whether it's an A or B, the place of the specimen that yielded this virus, such as in Perth, the sequential lab number in the laboratory there in Perth for the year, and the year. And sometimes we put that subtype after it. So a Perth 19-2009 virus is a typical type of virus that comes up in our nomenclature. What are the important characteristics? Well, they have this single-stranded RNA gene or blueprint, genetic blueprint. What does that mean? Well, most life forms actually have double-stranded DNA genes. Off those, we read the RNA, which then becomes a template for making proteins, which are the building blocks of our bodies and our cells. Now, this is important because with that double-stranded DNA, when we replicate our cells, it's like setting up a new email account or something of that nature, where you're asked to enter a password and then confirm the password, and you have to get it right before it's accepted. And the cell can use this to actually correct any mistakes that's going on when the DNA is being replicated. Whereas with replicating single-stranded RNA, you can enter your password, if you like, and make a mistake, and that gets locked in there for all time. So that becomes a mutation in the context of a virus, and it will continue to mutate and accumulate mutations. And these cause the changes in the surface proteins of the virus. The genetic material is segmented in separate genes, as I've said. That gives the potential for ready genetic mixing or reassortment, where you get two viruses into the same animal and cells. And that's where we get this mixing between animal and human viruses, which can give us these new pandemic viruses. I'm not going to talk much about pandemics. And it's an enveloped virus. It's got a baggy envelope structure. And what I've tried to liken it to here is sticking toothpicks into a lemon or an orange, and the virus doesn't mind. You can put them anywhere, and it doesn't matter what they look like if they change. So the virus is very accommodating to changes in its proteins. And if we compare that with poliovirus, for example, which is a highly structured virus, you can view that more like a three-dimensional jigsaw puzzle. And if one of the pieces is wrong, the whole thing just doesn't fit together. So the changes in the poliovirus are very hard to achieve. In influenza viruses, they're very common. Immunity to influenza, well, we do have some natural resistance. You can, by being healthy, it doesn't really protect you against an infection. But by being unhealthy, it certainly makes you more susceptible. So people with malnutrition, for example, are more susceptible to infections. People who smoke are more susceptible to infections. And I've just shown little pictures of those cilia, the little beating hair-like structures on your respiratory tract that keep it nice and clean, what happens in smokers, they're stunted, they don't function properly, and so you get things laid down in the respiratory tract, not swept away, so the greater chance of infection. But most of our immunity is acquired specific immunity. It's antibodies that are derived from infection or vaccination in the case of influenza. And what I'm trying to show here with this model, let's pretend the virus has got key-like structures on the surface. These are the surface proteins. And we make antibodies that fit against these keys and bind against them and stop the virus from actually infecting cells. Now, when the virus mutates, it changes those key-like structures, and when the antibodies come along, they can't grip properly to those surface structures, and so they become less effective or ineffective at protecting us. So this is why we have to keep updating our vaccines to accommodate that. How is influenza transmitted? Well, this is how it's transmitted. If you backlift somebody in an elevator and they coughed, this is what you'd see, all these nasty little droplets coming out from their mouth as they cough or even as they sneeze. And inside them, they may well be carrying influenza viruses. And there are three methods by which we can contract influenza. The little particles that stay in the air for a while, travel a few meters, breathe them in, it infects your respiratory tract. Bigger droplets, they travel a shorter distance and they stay in the air for a much shorter period of time, and they can get deposited on surfaces. And you can deposit material, viral-containing material on surfaces by your hands, by blowing your nose, coughing into your hand, and then touching something. Typical things around an office: keyboards, telephones, photocopiers, door handles. These are all ways that you can become infected, and the virus can live on those surfaces for quite some time. If we look at transmission of influenza, from the time that you're infected, as shown by the red star here, you very shortly after that start to produce virus in your respiratory tract and to shed it from your respiratory tract. So from a very early stage, you're shedding virus, but you really don't develop symptoms such as the fever, the aches and pains, the things that are going to actually make you go home and go to bed if you're wise. So there's this period of about a day where people can be shedding influenza virus before they really develop symptoms and are aware that they are in fact ill.